This is the second video, part 2 video for rational exponents. In the previous video, we saw how we can express a radical as a rational exponent and a rational exponent as a radical. We also saw the rules of exponents, reviewed the laws of exponents. So here we're going to apply those laws of exponents. Example number 1, we have two bases, same basis, different exponents, and there's multiplication operation in the middle. So laws of exponents says that we can go ahead and add the exponents. 2/3 plus 5/6. In order for me to be able to add these fractions, the denominators have to be same. So I need to multiply both numerator and denominator with the 2 for the first fraction. Turns out to be 4/6 plus 5/6, which is 16 to the power 9/6. Okay. 16 to the power 9/6. Let's go ahead and simplify 9/6. That comes out to be 3/2. We can divide both numerator and denominator with a 3, so 3/2. And if I write it as a radical, this is square root of 16 raised to the third power. Square root of 16, the denominator of the fractional exponent becomes the index, and the numerator becomes the exponent. Square root of 16 is 4. 4 to the third power is 64. And that is example number 1. So this expression simplifies to 64 with no exponent. Here's example number 2. Same base, different exponents, and we have a quotient. So the rule says we can subtract the exponents. 2/3 minus negative 5/6. Now, there's two negatives here. They are going to multiply and become positive. 2/3 plus 5/6. Again, we need the common denominator. So that turns out to be 4 to the power 4/6 plus 5/6, which is 4 to the power 9/6, which is 4 to the power 3/2. Again, square root of 4 to the third power. That's what it simplifies to, square root of 4 to the third power. Square root of 4 is 2. 2 to the third power is 8. So this expression simplifies to 8. Next, example number 3. We do have the quotient rule here, but before that, because both my numerator and denominator exponents are negative, I'm going to take the numerator to the denominator and denominator to the numerator to make my exponents positive, and then I'll deal with the positive exponents. Bases are same and I have a quotient. I can express it as a single base with the difference of the quotient. Turns out to be 5 to the power 3/4 minus 1/3. We do need the common denominator, so I'm going to multiply first fraction top and bottom with a 3, second fraction top and bottom with a 4. So that's 9 take away 4 divided by 12, which is 5 to the power 5/12. Now, can we simplify this any further? Not really. If we want, we can write it as 12th root of 5 raised to the 5th power, but it's also okay to leave it in the fractional exponent. Now you might wonder, how do you know which form is good to leave your answer in? If it's not stated in the problem, then if your problem has the exponents, then leave your final solution with the exponents. If your problem started with the radicals, then leave your final solution with the radicals. Next example, here we have a power to a power, so the exponents are going to multiply 3/2 times 5/3, and once we simplify, it turns out to be 7 to the power 5/2. Again, cannot be simplified any further. If I do square root of 7 to the 5th power, square root of 7 is not a perfect square, so I won't be simplified any further. I'm going to leave it right there. If you want, you can go ahead and find it on the calculator. On the calculator, button for the exponent usually looks like this, or it's something like x to the empty box or x to the power y. Different calculators have different notation for expressing an exponent. Okay, that was example number 4. Here's number 5. We have two bases inside and an exponent outside. The outside exponent is going to multiply with inner exponents. So 8, 1 times 2/3. 8 had the exponent 1. X to the power 5/6 times 2/3. Okay, let's go ahead and simplify. So it becomes cube root of 8 to the second power, and we can simplify x to the power 5/9 after we cancel 2 and the 6. So that leaves me with cube root of 8 is 2, 2 to the second power is 4, x to the power 5 nines. And that would be our final product and product to leave my solution in. Next example, I do have two bases inside with exponents, and there is an exponent outside. The inner exponents are going to multiply with the outer exponent. Turns out to be a to the power 3 halves times 8, b to the power 1/4 times 8. Okay, let us simplify here. That would be 2, and that would be, so it turns out to be a to the power negative 12, because negative 3 times 4 is negative 12, b to the second power times b to the second power. So b square over a to the 12th power, because we have a negative exponent, it's a norm that we don't leave our final solution with the negative exponent. So we either bring them to the denominator to make them positive, or if you have a negative exponent in the denominator, we take it to the numerator to make it positive. Okay, next problem. Here we have multiple things going on. First of all, there's two parentheses. In the first parentheses, I don't have two of the same bases, and there's not a whole lot to do in the first parentheses, so I'm going to leave it like this. And the second parentheses, this outer exponent is going to multiply with inner exponents. Okay, let's go ahead and simplify this. So x to the power negative 4/3 times y to the power negative 2. And there's a hidden multiplication in here, so I'm just going to write them with the multiplication. X to the power 8/3, y to the power 2/3, because we can cancel there. Now we have the two of the same bases, different exponents, and there's product in the middle. So exponents are going to add up. 8/3 plus negative 4/3, and then y to the power negative 2 plus 2/3. Turns out to be 8/3 minus 4/3 is 4/3. Y to the power negative 6 plus 2. We need the same denominator, so we will have to multiply top and bottom with the 3 here. Negative 6 plus 2 is negative 4/3. Now, negative denominator, negative exponent will go to the denominator and become positive. So x over y to the power 4/3 is what we're left with. Final product and product, okay? Example number 8. So a lot going on here. We have a numerator with multiple bases inside, and they have exponents and so we have a power to a power in the numerator, and we have denominator with different bases and exponents. Let's start with the numerator, because there is more to do in the numerator. So this outer exponent is going to multiply with every single exponent inside. 2 to the 5th power, x to the negative 5th power, y to the 2/5, y to the second power over x squared, y squared. I do have a y squared in the numerator, y squared in the denominator, so that'll be gone. And I also have a negative exponent in the numerator for x, so I'm going to bring it to the denominator and make it positive. 32 divided by, exponents will add. In the denominator, I have same bases, different exponents with the product in the middle. 32 divided by x to the 12th power. Number 9, simplify b to the power 1/2, b to the power 3/4 over negative b to the power 1/4. This is just negative 1 sitting in the front. It's not an exponent, okay? All right, so we can add the exponents for the numerator. Two halves plus 1/2 plus 3/4 minus 1/4. We need to have common denominators. So that turns out to be 5. 5 minus 1 is 4/4, which is equal to 1. So negative b is what we are left with here, or negative b to the first power. Number 10, we can simplify them. Either we can write them as a exponent first and then simplify, or we can write them as a radical and then simplify. We have seen how to simplify these as a radical, but right now I'm going to write them as an exponent and then go ahead and use the rules of exponents to simplify. So okay, this outer exponent is going to multiply with every single exponent inside, so that turns out to be cube root of 27. 3 times 1/3 is 1, 9 times 1/3 is 3. 3ab to the third power. Number 11. Okay, let's take care of the numerator first. M to the second power times 1/4 n to the power 1/4 divided by m to the power negative 1/2 n to the power 5/8. M to the power 1/2 n to the power 1/4 divided by m to the power negative 1/2 n to the power 5/8. So let's go ahead and, because we have a quotient and we have the same bases in the numerator and denominator, we can try to write them as a single. Instead of a quotient, the exponents will subtract 1/4 minus 5/8. Okay, so this will become a positive, and we do need the common denominators for the n's here. So it turns out to be m to the power 1/2 plus 1/2 is 1, and n to the power 2 minus 5 is negative 3/8. Now negative exponent can be brought to the denominator and made positive, and that would be all we can do with this problem. Number 12 says simplify, so we're going to be distributing distributive property. Remember, when we are distributing, we are multiplying, so x to the power 1/2 times x to the power 1/2 turns out to be, let's just write it as x to the 1/2 times x to the 1/2 plus x to the 1/2 times x to the 3/2. So this turns out to be x to the power 1/2 plus 1/2 plus x to the power 1/2 plus 3/2. Because the bases are same and there's product in the middle, so we can use the rule of exponent here. Turns out to be x to the power 1 plus x to the power 4/2, which is x squared. So x plus x squared is what we're left with here. Here's number 13. Y to the power 2/3 plus 5 times y to the power 2/3 minus 5. FOIL, first, outer, inner, last. So first times first, y to the power 2/3 times y to the power 2/3. Outer is negative 5, y to the power 2/3. Inner, positive 5, y to the power 2/3. Last is positive 5 times negative 5, which is negative 25. So it turns out to be y to the power 2/3 plus 2/3. Exponents will add. Positive and negative of the same thing will cancel. 2/3 plus 2/3 is the denominators are same. Turns out to be 4/3 minus 25. Now, if you want, you can simplify it a little bit more, because this is same thing as y to the 4th power cube root minus 25. So we can say this is y cube root of y minus 25. And both ways it's correct. Factor out an x to the power 3/2 from x to the power 5/2 minus x to the 3/2. This one you have to stop for a minute and think about. X to the power 3/2 is what you want to factor out. 3/2 times what will give you x to the 5/2. Think about 3/2. 3/2 is 1.5. 5/2 is 2.5. So 3/2 plus 1 is actually 5/2. So that's just in the scratch. I know that. Just knowing the fractions. So 3/2, if I multiply with x to the first power, when I distribute, I would be able to get x to the 5/2 back. So it turns out to be x to the 3/2 times x minus 1. Next example, number 15. 3 to the power 1/2 times 3 to the power 3/4 divided by 3 to the power 1/4. Well, for the numerators, exponents are going to add, and for the denominator, they're going to subtract. You can split it into two different steps. You can take care of numerator separate and turn it into a single expression and then take care of the denominator. I'm just trying to do it together to save time, which is totally fine. So we need the common denominator. That would be 5/4 minus 1/4, which is 4/4, which is equal to 1. That turns out to be equal to 3. Okay. We use the rational exponents to simplify. So 9 to the power 3 6, 9 to the power 1 1/2, which is square root of 9, and that's equal to 3. So I'm writing these as rational exponents and simplify. The x cube root is the same thing as exponent 1/3. Square root is same thing as exponent 1/2. Now we can multiply the exponents, and this can be written as n to the 6th root of n. Okay. Next, so x to the power 3/4 over x to the power 1/2. We can subtract the exponents because the bases are same. 3/4 minus 2/4 is 1/4. So x to the 1/4, which is 4th root of x. 12th power, a to the power 8 over 12, b to the power 4 over 12. Just writing it as the exponents instead of the radicals. Let's divide numerator and denominator with 4. Numerator and denominator with 4 here again. So it turns out to be a to the power 2/3, b to the power 1/3, which can be also written as a squared b cube root. Okay. Next we have number 19, 8th root of 4y squared. So 4y squared to the power 1/8. Well, let's write 4 as 2 squared. 2 squared to the power 1/8, y squared to the power 1/8. Y, so exponents multiply. Y exponent 2 times 1/8. So this would be a 4, this would be a 4. So 2 to the power 1/4 and y to the power 1/4, which is 4th root of 2y. Okay. Use the rational exponents to write as a single root. So a couple more examples. Here we're going to be using the rational exponents to write as a single radical here. So b to the power 2/3 in the numerator, b to the power 1/4 in the denominator. We can subtract the radicals. We can subtract the exponents here, and we need the common denominator. So multiply first fraction with a 4, second fraction with a 3. So 8 take away 3 is 5/12. So we can express it as a single radical, b to the 5th power 12th root. We have 5 to the 1/3, 2 to the power 1/2. So 5 to the 1/3, 2 raised to the power 1/2. What can we do over here? Well, one thing we can try is we can express them both. Doesn't look like we can do a whole lot, but we are asked to write it as a single root. So I'm going to get both of the exponents with the same denominator. So I'm going to multiply top and bottom with the 2, top and bottom with the 3. 5 to the power 2/6, 2 to the power 3/6. So now I can do 5 to the 2nd power, 2 to the 3rd power, 6th root. Okay. That looks like it would be a single radical. If you're bothered by 5 square, you can do 25 times 8, which is 200. No, 25 times 8 is going to be 200, right? 6th root of 200. So we wrote it as a single radical. Next, last example, x to the power 1/3, x to the power 1/4, x to the power 3/8. I just wrote, instead of radicals, I wrote the exponents, and now we can add all the exponents because the bases are same and there's product in the middle. So my common denominator here would be 8 and 4 and 3. Looks like it would be 24. So I need to get a common denominator as 24. So I'll multiply the first fraction top and bottom with an 8, the last one with a 3, the middle one with a 6. Turns out to be 8 plus 6 is 14. That would be x to the power 17 over 24. And as a single radical, this is x to the 17th power with 24 index in the root. That's all about rational exponents. So this was the second video in series of rational exponents.